Okay, and some operations are their own inverse. So for example, a reflection, right? If you reflect through a mirror plane 2 times, then that's the equivalent of doing nothing. So a reflection is its own inverse. Another one would be an inversion, right? If you invert the molecule twice, that's the same as doing nothing. Inversions. And also the C2 operator, right? So if you rotate 180 degrees and then rotate again 180 degrees, that second 180 degrees undoes the first 180 degree rotation, right? Because you just end up rotating 360 degrees, which means you don't do anything. Okay, so these are their own inverse. Okay, I'm going to switch markers one more time. Okay, so that brings us to the next very important topic, which is groups. So in general, the set of symmetry operations belonging to a particular molecular geometry, you can prove that they form what in mathematics is called a group. And a group is a set of elements that are related by a combining operation. And in order for a set of elements to be a group, it has to obey a very specific set of rules. Okay, so first, it has to have the property of closure. And closure means that if P and Q are in the group, then P times Q is also in the group. Okay. The second requirement is the group has to have, or the elements of the group have to be associative. So if so that basically says that P times Q, right? This combined operator operating on R has to be equal to if you operate P on the operator that you get when you operate Q on R. Okay. The third requirement is that each element of the group also has to have its inverse in the group. So the inverse rule says that if some operator R is in the group, then R inverse has to be in the group. Right, and by definition, of course, it has to have the property that R inverse times R is by definition identity. Okay, and a corollary of rule number 1 and rule number 3 is that it's usually included as its own rule, because it's very important, and that is the identity rule, which says that the identity operator E has to be in the group. Okay? Okay, and so this concept of groups, this is an abstract mathematical concept that you'll come across if you take a course about abstract algebra. And groups are mathematically very, very general. So you could have, if you're a mathematician, you might consider some examples of groups, including, for example, you could have a group with a finite number of elements, and that would include the set of numbers 1, minus 1, I, right, the imaginary number I, and minus I, under the combining operation of multiplication. Right, and you can go through this set of rules. You can see that for each pair of elements of the group, if you multiply two of them together, the result is also a member of the group, right? So 1 times minus 1 is 1, for example. Minus 1 times I gives minus I, which is also in the group. I times itself gives minus 1, which is in the group. I times minus I gives positive 1, which is also in the group, and so forth. Associative law, of course, holds because multiplication is associative. The inverse of each operator is also in the group, as you can prove to yourself, right? Minus 1 is its own inverse. I and minus I are the inverse of each other, because if you multiply them together, you get the identity operator 1. And then, of course, the identity operator 1 is an element of the group. Okay, you can also have infinite groups. So another example, so one example would be this one. Another example would be the set of all integers under the combining operation of addition. And again, you can prove to yourself that this is indeed a group. So if you take any integer and add it to another integer, you get some integer, right? So it has closure. Addition is, of course, associative. It follows the associative law. If you so the identity would be adding the number 0, right? Addition of 0 leaves any integer unchanged. And the inverse of each operator is also an operator in the group. Because, for example, adding plus 3 to any integer is the inverse of adding negative 3, right? And both of those are in the group, right? So the inverse of each integer would be its negative. Okay? Okay, and so, yeah, these would be sort of, mathematical groups that a mathematician might care about. But in chemistry, the most important type of group theory is point group theory. And so a point group, by definition, this is a group whose elements are the symmetry operators, the set of symmetry operators of a molecule. And to give you a concrete example, let's look at a simple molecule We can do water. And again, if we choose the axis system where x is coming out of the plane of the board, out at us, then the group that, or the point group that describes all the symmetry operations that, all the symmetry operators of the water molecule, this has a name, it's called C2V, C subscript 2V. And the operators that belong to the C2V group are the identity operator, of course. It's got a C2 operator, right? Because you can rotate through the axis that bisects the HOH bond, right? You can rotate 180 degrees around that axis. That's a symmetry operation. And it's also got two reflection planes. It's got a sigma V in the XZ plane, right? So you can reflect across this plane here, or it's got a sigma V in the YZ plane, right? Which that would correspond to reflecting in the plane of the board. Okay, and you can check, you can verify that indeed this set of operations is a group under the combining operation of applying the operators consecutively by looking at the multiplication table of the group. So if you take all the elements of the group and multiply them by all the elements of the group, right? So E, C2, sigma V, XZ, and sigma V, YZ. Then basically if you take any operator and then operate identity, you get that same operator. And the same applies along this column. You're also just going to get C2, sigma V, XZ, sigma V, YZ. Okay, so if you rotate 180 degrees and then rotate 180 degrees again, you get the identity operator. If you do a sigma V in the XZ plane, then you would basically exchange hydrogen 1 and 2. And if you then did a C2 rotation, you would exchange hydrogen 1 and 2 back again, but you would reverse the direction of the x-axis. And so doing this operation followed by this operation is equivalent actually to sigma V YZ, which reverses the direction only of the x-axis. So here we'd have sigma V YZ. And by similar arguments, sigma V YZ, if you operate that followed by C2 operation, you get sigma V XZ. And you can check the rest of these yourself, but I'll just fill out the rest of this table. Here you get sigma V YZ. Here you get sigma V XZ. Here you get E. Here you get C2. Here you get C2, and here you get E. Okay, so you can verify the other elements of this table on your own. But one thing that you'll notice about this table is that the multiplication table is symmetric, right? So if we sort of reflect the multiplication table about the diagonal, then it looks like its own transpose. And so what that tells you is that if you first do a C2 operation and then you do a sigma V XZ, that's the same as if you first do a sigma v x z and then you do a C2, right? These two elements are the same. And so C2V group is actually an example of what's called an abelian group. And an abelian group this is defined as a group whose elements commute. Okay? So a couple other important terminologies involving groups. Two groups are said to be isomorphic if there is a one-to-one mapping of the multiplication table. So basically, if I have a group, you know, A, B, C, right, and some other group, you know, A prime, B prime, C prime, right? If I can map A to A prime and C to B prime and B to C prime, and vice versa, right? And if you just take the multiplication table for the group, and every time you see an A, instead you substitute A prime, every time you see a B you substitute C prime, and so forth. If you can do that mapping, do that substitution, and obtain the multiplication table for the other group, then these two groups are said to be isomorphic. The two groups are basically equivalent to one another, in a sense. But sometimes you have two groups which have a different size, right? They have a different number of elements. And in that case, they can't be isomorphic, but in some cases they can be homomorphic. And two groups are said to be homomorphic if there exists a many-to-one mapping of the multiplication table. Okay? And a specific example of that would be if you have the C2V group, right? The C2V group. Actually, let me make a little bit more space. Okay, I'm going to come back over to the other side. Okay, so the C2V group, this contains the elements E, C2, sigma V, XZ, and sigma V, YZ. And you can also form a group by just taking the E and C2 operators. And you can show that these two groups are homomorphic if you make an equivalence between the E operators, between the C2 operators, and if you map the sigma V operator onto the E operator, and the sigma VXZ onto E, and the sigma VYZ onto C2. Then you actually, so in that case, basically, we can do that, right? So if you apply the mapping to this multiplication table here, then E gets mapped to E, C2 gets mapped to C2, sigma VXZ gets mapped to E, sigma VYZ gets mapped to C2. And if you apply the same mapping to all these elements of this table, then you're going to see that the table that you get looks like this. And this is indeed a, it looks redundant, right? Because we've included the operators 2 times, but this is a correct multiplication table for the group containing just E and C2, right? Anytime you have a C2 times a C2, right? C2 is its own inverse, so you get identity. Anytime you have identity times C2, you get C2, as you would expect. Okay, another important concept is the concept of classes. So members of a group can be divided into classes. And by definition, P, an operator P and an operator R belong to the same class. If for some operator Z that's also a member of the group, if P equals the inverse of Z times R times Z. This transformation where you multiply an operator on the left by Z inverse and on the right by Z, this is a special type of transformation called a similarity transformation. Okay, for some Z in the group. Okay, and this here, this has a special name. This is a similarity transformation. Okay, and so we can look at an example. So if you consider ammonia, right, NH3. Right, this has a trigonal pyramidal geometry. We're not going to consider the inversion of like the umbrella inversion. We're just going to consider this as a rigid structure. Okay, ammonia belongs to a point group called C3V. And the operators of the C3V point group are identity. There's a C3 axis, right? So the axis that goes right through the center of the molecule here, this is a C3 axis. You can rotate by 120 degrees about this axis and leave the molecule in an equivalent configuration. You also have a C3 inverse, right? So rotating by minus 120 degrees. And there are 3 different sigma V planes of reflection. I'll call them sigma V prime, sigma V 2 prime, and sigma V triple prime. Okay, and these reflect the molecule in a plane containing the NH1 bond, right? That would reflect H3 onto H2, right? Sigma V double prime reflects in a plane containing the NH2 bond and bisecting the other, the H1N H3 bond angle, right? That would exchange H1 with H3. And then the sigma V triple bond, this would be in a plane containing the NH3 bond. Okay, and okay, so let's ask ourselves, which elements of this group might belong to the same class. Well, we can take so actually the identity operator is always in a class of its own, right? Because anytime you take an inverse operator times identity times an inverse operator, doesn't matter which operator it is, identity operates on the operator to give itself. You just have an operator times its inverse, which gives identity. So you're never gonna, the identity operator is always just gonna be in a class by itself. But if we consider the C3 operator, okay, what happens if we operate the C3 inverse similarity transformation? So the inverse of that would be C3, and itself would be C3 inverse, right? This is going to give, okay, so C3 times its inverse is going to be identity, so this is just going to give C3. Okay, if we operate the C3 operator, right, if we take the similarity transformation using the C3 operator, then we're going to get C3 inverse on the left and C3 on the right. This again is going to give just C3, right, because C3 inverse times C3 equals identity. However, if we take the sigma V prime operator, and so sigma operators are always their own inverse. So the similarity transformation using sigma V prime is just going to be right and left multiplying by sigma V prime. And now this is a little bit more complicated. So let's think about this. So if we apply this operator to the ammonia molecule, then basically we would have N, H1, H2, H3. So if we first operate sigma V prime, right, that's a plane of reflection through the plane of the board, basically. So that's going to leave H1 in the same position, but it's going to map H3 onto where H2 used to be. And H2 is going to end up where H3 used to be. Okay, and then we have to do a C3 rotation, so a clockwise rotation of 120 degrees. Okay, so if we do a C3 rotation, then we end up, the H2 gets rotated to where the H1 used to be. The H1 gets rotated to where the H3 used to be. And the H3 gets rotated to where the H2 used to be. Okay, and then we need to do one additional sigma V prime. So now it's still going to be in the plane of the board, right, where the NH bond initially was, right? And so now sigma V prime, that's going to give us, it's going to leave the H2 where it used to be, but it's going to invert, or it's going to reverse the H1 and the H3. So we're going to get an H1 coming out towards us and H3 going back into the plane of the board. Okay, and now we can see that this combined operation, these combined 3 operations, basically they, let's see, what did they do? They basically rotated the molecule counterclockwise by 120 degrees, right? So H1 overall got rotated 120 degrees to end up here. H3 got rotated to end up back here, and H2 got rotated to end up back around here. So these three operations, if you multiply them together, they end up giving C3 inverse. And by similar arguments, you can show that sigma V double prime times C3 times sigma V double prime, this is also equal to C3 inverse, and sigma V triple prime times C3 times sigma V triple prime, this is also equal to C3 inverse. Okay? And using similar arguments, right, I'll let you work out the operator algebra by yourself. You can go through this and convince yourself that it's true. But if you apply similarity transformations involving all of the group elements to the sigma V prime operator, so if we apply C3 inverse, this ends up giving us sigma V double prime. If we apply the inverse, right, C3 inverse, C3, this ends up giving us sigma V triple prime. If you apply sigma V prime similarity transformation to sigma V prime, you get just sigma V prime. That one's probably easy to see why that's true. If you apply sigma V double prime on the left and right, you get sigma V triple prime. And just one more, if you apply sigma V triple prime on the left and right, then you get sigma V double prime. And so this lets us conclude that, so basically C3 and C3 inverse have to be in the same class as one another, right? Because they get transformed into one another by these similarity transformations. And all three sigma V prime, double prime, and triple prime operations are in their own class. They're in another class. Because basically the operations of the point group, when you apply similarity transformations involving those operators, they map sigma V prime into sigma V double prime and sigma V triple prime. And, you know, vice versa is also true. Okay. So that actually concludes chapter 2 of your textbook, chapter 2 of Bernath. We have a little bit more time remaining, so I'm going to go ahead and start on a little bit of chapter 3. Actually, before I do that, I'll just show you one thing on the computer.